Here's usual starter, 4 questions, pause the video, and then I want you to complete the questions and then I'll go over them just now, okay? So, question 1, what is meant by a volatile molecule? Well, it's a molecule that is easily evaporated, okay? You should know the term volatile by now, easily evaporated. Explain why broccoli is cooked in water, okay? So, nice and simple. Hopefully you've been looking over your notes. So broccoli contain non-polar flavour molecules. Okay? Non-polar flavour molecules and are cooked in water. And again, you need to know that water is polar. Okay, it is cooked in water so that the flavour molecules do not dissolve in the water. Okay, now remember, if broccoli contains non-polar flavour molecules, if water's polar, it means, remember, polar does not dissolve non-polar, so the flavour molecules are kept within the broccoli, okay? So flavour molecules do not dissolve in water, and just remember, polar molecules do not dissolve non-polar molecules. Okay, and that's it. That's it. Right, question 3. What molecule would be more volatile, CH4 or C10H22? And the answer for that is, it's going to be CH4 will be more volatile, but explain our answer, okay? So CH4, there's going to be weaker or less LDFs between molecules. Okay, because it's smaller, obviously if it's smaller, if it's only got one carbon, it's going to have less LDF, so they're going to be weaker. So that means the less energy is required to break the LDFs. Okay, if there's less energy required, that means they're going to make them more, it's going to be more volatile. Okay, now obviously CH4, that's methane gas, that's not a flavour molecule, but if it were a flavour molecule, because it's more volatile, that would give it more flavour, okay, if it was a flavour molecule, obviously. This one here, C3H8 or C2H5OH, what one's more volatile? It is going to be that one, but the question is, why? Well, C3H8, if we look at that, there's no functional group, okay, no functional groups, so that means there's going to be no hydrogen bonding, okay, whereas in ethanol, C2H5OH, because we've got that hydroxyl group, we're going to have hydrogen bonding, okay, but because we have no hydrogen bonding, it contains only LDFs, okay, and because it contains only LDFs, again, less energy needed to break, and because there's less energy, it is more volatile, okay, and that's it. Again, C3H8, which is propane, if that were a flavour molecule, if it's more volatile, it would mean more flavour, okay? And in question 4, why can the molecules in 3B be compared? Okay, now you need a full answer here. They've got a similar GFM, okay, but that's not enough. You have to expand a wee bit further. Similar GFM, therefore similar number of electrons, and finally if we've got a similar number of electrons, we've got a similar strength of LDFs. Okay, because what we're comparing there is the difference hydrogen bonding makes. Okay, they've both got LDFs, obviously. Okay, because they've got the same similar GFM, a similar number of electrons, they're going to have a similar strength in LDF. So the LDFs make no difference there. The only difference is going to be this hydroxyl group, which contains hydrogen bonding. Okay, so that's why we're able to compare it. You can't just say similar GFM, you have to expand it. Right, so what we're going to do, we are going to finish off Unit 2 today, and we are going to do chemistry of cooking. Okay, and that is lesson 2. Okay, so this is the final lesson of Unit 2, and that will be us, we'll complete it. So what we're going to look at, a sort of subheading, is we're going to look at changes in protein structure in food. Okay, now the good thing about this is you guys already know this. Yeah, we've already done it. We've done proteins. Yeah, you're going to be experts on this. So what we're going to do, we're going to do just a little recap, and then we're going to start looking at cooking eggs and cooking like steak and meat, stuff like that. Okay, so first things first, proteins are made, hopefully you know what proteins are made from, but proteins are made from amino acids. Yeah, remember, amino acids are the building blocks of proteins. Proteins are made from amino acids in condensation, and remember, proteins are polymers, so it's condensation, polymerization reactions. Okay, you need to know that. Right, now, between protein polymers, okay, I'll highlight that, polymers, okay, and remember it is between, so between protein polymers, there are hydrogen bonds due to the amide / peptide link. Okay, and hopefully you remember that the amide peptide link, that is the functional group of a protein. Okay, and the reason that we're getting hydrogen bonding is because of that. Okay, the hydrogen is covalently bonded to nitrogen, oxygen or fluorine, nitrogen in this case, and you're going to get hydrogen bonding between this and another amide link. Okay, that bond isn't the hydrogen bond. The hydrogen bonds are forced, and it's between the other amide link. Okay. Right, so that's a recap. Obviously, I've not recapped all of proteins because I've not spoke about enzymes or hydrolysis or whatever. But yeah, that's just a recap of what we need to know for this next bit. Okay, so what we're going to look at, we're going to look at cooking eggs. Okay. Now again, you already know this, you just haven't applied it. Okay, so let's make a wee note here. So proteins in eggs are globular. Okay, now you should know what a globular protein is. Globular, it's tertiary or quaternary if you want to go further, but we'll just stick with tertiary. Tertiary complex, okay, very complex, they all like intertwined each other, blah 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 blah, okay, so complex, they are wrapped around each other in a ball-like structure. Okay, and the important thing is they are held by hydrogen bonding. Okay, and we're getting hydrogen bonding again because of that NH in the amide link. Okay, so very similar. Remember, very similar when we talk about enzymes. Yeah, enzymes are proteins. The proteins found in eggs are, they work exactly the same way. So when heated, the energy, okay, the energy breaks the hydrogen bonding, and the protein chains unwind. Okay, so at this stage we would call them, they're denatured. Okay, they're denatured because they've changed shape. Okay, that's what denaturing means. It can be applied to enzymes, it can be applied to any sort of protein. Okay, they are denatured. Now, again, very much like what happens in enzymes, proteins then form hydrogen bonds with different chains to form large structures with different shapes. Okay, and because of that, that causes the egg white, yeah, in eggs, the egg white, I can't remember the name of it, I think it's like albumin or something like that. It causes the egg white to solidify. Okay, and that's what's happening when you're cooking an egg. What's happening when you put it into the pan, it starts to heat up, the hydrogen bonds are breaking, yeah, the protein chains are unwinding, and then they start to form other hydrogen bonds to different chains, and then you can see the egg start to turn white. That's why, okay, because it's forming different hydrogen bonds to different structures, and it's causing it to solidify. Okay, right, next one we're going to look at is we're going to look at cooking meats. Okay, so again, this is identical to what you already know. It's identical to eggs, but you still need to know it. Okay, now meats, you know, steak, blah blah blah, contain fibrous proteins. Okay, now by fibrous we mean linear, yeah, primary, secondary proteins, and you probably already know this, or you might know it, called collagen. Okay, now collagen, the protein found in meats that helps like sort of bind the muscle, strengthen the muscle. So what happens, again, identical to what you already know. So when heated, hydrogen bonds break and proteins unwind. Okay, they become denatured. Now, again, they reattach in different ways, obviously via hydrogen bonding. It's all about hydrogen bonding with proteins, okay? So they reattach in different ways via hydrogen bonding to give different textures, okay? And that's it, yeah? I suppose we could add a wee bit extra if you're interested, which I always find interesting, okay? A wee bit extra. The length of heating, that determines the texture of it, okay? So length of heating determines the texture. Okay, so what I mean by that, for example, steak, you could have rare, you could have medium rare, you could have medium well done, okay? So you could have rare, medium rare, medium well done, etc. Yeah. Blue steak if you're an absolute maddo. So yeah. So length of heating determines the texture, so you get rare, medium, well done, blah blah blah. Okay. Right. What we're going to do now is we are going to look at the final section. Okay, so that's us done with the cooking part. We are going to look at antioxidants. Okay. So it shouldn't take long this. Right, now, what you need to know before we start looking at antioxidants, you need to know the definition of oxidation. Okay, now, oxidation, it's got two definitions. It is the loss of electrons, okay, and we spoke about that, or the increase, again this is more sort of oxidation of alcohols, aldehydes, etc., or increase in the O to H ratio. Okay, you do need to know both. Yeah, both are very important. But yeah, so oxidation is the loss of electrons or the increase in the OH ratio. Okay, oxygen to hydrogen ratio. Now, so what happens? Helps if I can spell oxygen. So the oxygen from the air, okay, causes the oxidation of food and drink. Okay, so the oxygen from the air, that's causing all your sort of, in fact, every sort of food and drink to begin to oxidise. Now this is the important part, okay? The oxidation, okay, you need to know this, I'll highlight this as well. So the oxidation of edible oils and fats, yeah, we've done fats and oils, edible oils and fats give a rancid flavour, okay, and that's a key word there, rancid flavour, so I'll highlight that. The oxidation of edible oils and fats give a rancid flavour. It causes the food to go off, and I don't know if you've ever had anything that's went off, you know, milk or like an apple or something. It's not really nice. So I'll give you a wee example. Let's look at wine. Not that you guys will know this, of course, but if you look at wine, wine's obviously an alcohol, yeah, contains hydroxyl groups. And what happens if we oxidise, yeah, the air over time, if you leave wine sitting out, the oxygen from the air will oxidise that, and because it's an alcohol, that would oxidise it first to an aldehyde, but then eventually to carboxylic acid. Yeah, and if you're drinking carboxylic acid, it is absolutely horrible. Okay, and same with sort of fats, oils, and food. What can happen is obviously in the air you've got moisture, so the water and air hydrolyzes the fat and oil. Okay, so the moisture in the air hydrolyzes the fat and the oil, and you should know this already. Yeah, if you hydrolyze a fat and an oil, you're going to get glycerol, and you're going to get 3 fatty acids. Okay, now again, the glycerol can further oxidize into a carboxylic acid, and then the 3 fatty acids as well, they're rancid. Okay, horrible. So that's what's happening. Yeah, the oxygen from the air is causing oxidation, it's causing foods and drink to go off. Yeah, giving that rancid flavour. Very important, rancid flavour, edible fats and oils. Okay, now let's start talking about antioxidants. Now antioxidants are amazing, actually. Yeah, and the name kind of gives it away. You've probably already worked out what an antioxidant is, but antioxidants are added to food/drink as they are molecules that, sorry, that's my dog. The doors just went. Antioxidants are added to food/drink as they are molecules that prevent unwanted oxidation reactions occurring. Yeah, so antioxidants prevent oxidation. They are the opposite. Okay, so antioxidants prevent oxidation reactions from occurring. So that's why we add them into food and into drink. It's to prevent that oxidation process from happening, or not prevent it, slow it down. Okay. Now, antioxidants, they are reducing agents. Okay, now we've done reducing and oxidizing agents. Okay, so they are reducing agents, therefore they cause the compound they are added to. Yeah, so they cause the compound they are added to reduce. Okay, so if they are reducing, that means they are gaining electrons. Okay, remember what we mean by oxidation. Oxidation is the loss of electrons. Okay, so we want to prevent the loss of electrons. So what antioxidants do is they give electrons. Okay, so they cause the compound to gain electrons, making, okay, so that makes making themselves oxidize, lose electrons. Okay, so I'll explain what we mean. So antioxidants are reducing agents. So what they do is they lose their electrons, okay, and those electrons that are lost are picked up by the food and the drink, and that sort of prevents the oxidation from happening. Okay. So we'll make a wee note on that. So by giving the food slash drink its electrons, the antioxidant oxidizes instead of the food slash drink. Okay, so it's very clever. Okay, so we add antioxidants, and essentially the antioxidants, they oxidize instead of the food and the drink, because the antioxidant is given its electrons. Yeah. Okay, so if we keep giving electrons to our food and drink, they'll never oxidize, so they would never go off. Okay. However, food does go off. So what's happening there? So let's talk about that. So obviously, if the food antioxidants are constantly given the electrons, this prevents oxidation. Okay, so this prevents oxidation of the food slash drink, but yeah, not forever. Okay, it doesn't prevent oxidation forever, and the reason it doesn't, because not forever, as the antioxidants will eventually run out of electrons. Okay, they don't have an endless supply of electrons. They'll provide as many electrons as they can, but eventually they're going to run out, and then when they do run out, the food and the drink, that will then oxidize, and then it will go off. Okay, so the antioxidants will eventually run out of electrons, so that means food and drink will oxidize and go off. Okay, they're going to have that rancid flavour. Yeah, that keyword, rancid flavour. Yeah. Now the last wee bit. So in redox reactions, the antioxidant is the substance undergoing oxidation. Yeah, remember, antioxidants are reducing agents, so they cause reduction, but themselves they undergo oxidation, so they are losing electrons. So an example of that is vitamin C. Okay, and you can find that in many sort of fruits and that. So vitamin C found in many fruits is an antioxidant. Yeah, it's a natural antioxidant in the case of fruits. So C6, H8, O6, so that's our vitamin C. And you don't need to know this equation, I'm just showing you what happens. That is losing electrons. Okay, so we're interested in the electrons, so vitamin C is an antioxidant and it's losing electrons. And then this is the important part. These electrons here are donated to stop oxidation of food slash drink. Okay, and that's it. That's how antioxidants work. They provide electrons to prevent food and drink from oxidizing. This is Van der Waal. Right, come on you, move. Oh, move. Right, right, so that's us finished. There's a wee bit extra. Again, you don't need to know this, but I find this quite interesting. Okay, now, I don't know if you've ever noticed, but yeah, like a crisp bag, if you get it at the shop, it looks very, very puffy, okay? And many a time when I was younger, I'd be like, oh my god, I'm going to get hundreds of crisps in here, and then you open it up, and you maybe get about 5 or 6, and just heartbreak. But there is a reason for that, okay? I always used to get angry at that, but now that I understand the chemistry, I don't get as angry. But crisp bags are filled full of, are filled full of nitrogen, okay? Now, if they're filled full of nitrogen, that means in that bag there's going to be no oxygen, okay? It's very clever. They're filled full of nitrogen, therefore the crisps inside take longer to oxidize. Always blew my mind that. Okay, so when you open up a bag, it's nitrogen that's inside. Okay, so the crisp takes so long to oxidize. It's obviously when you open them, obviously air can get in and they'll begin to oxidize. But yeah, that's it. So let's recap what we have learned. Let me get my stuff. So at the start we spoke about the changes in protein structure in food, but you already know that, yeah, all proteins contain hydrogen bonding. So when we're cooking eggs, obviously the proteins are globular. The hydrogen bonds break the energy when heated, break the hydrogen bonding, and the protein chains begin to unwind. Okay, they start to change shape. The proteins then form hydrogen bonding with different chains, and they're forming large structures with different shapes, and that's causing the sort of egg white to solidify. And it's the same idea with cooking meats. The collagen, again, that's the type of protein, fibrous protein found in meats. When we heat that, same thing, the hydrogen bonds break and the proteins unwind, they reattach via hydrogen bonding, and we get different textures. And obviously the length that you choose to heat your meat determines the texture of it. Okay, so in the case of steaks, you get rare, medium well done, etc. Chicken, if you cook chicken for a very long time, it can be quite tough, quite not very nice, so you've got to try and get that right. And this bit here, the last bit we did was antioxidants. Okay, now the oxidation of edible oils and fats that gives out rancid flavour, so we add antioxidants into food and drink to prevent oxidation reactions from happening. Okay, they are reducing agents, you do need to know that. Okay, so they cause the compound to reduce, and that causes the antioxidants to oxidize. Okay, now if the antioxidants are given the food and drink its electrons, the antioxidant is oxidizing instead of the food and drink, and that's important. That's what's preventing the oxidation. Okay, however, as we've mentioned, that's not forever. Okay, because eventually the antioxidants, they're going to run out of electrons. Okay, and the minute they run out of electrons, the food or drink will begin to oxidize. Okay, and that's it. Okay, antioxidants, vitamin C, very common antioxidant, loses its electrons. Those electrons are donated to the food and drink, and that prevents oxidation. Okay, right, we'll leave it there. Thank you.